Okay, kind of a short one today. Let's imagine we've got a projectile launched from the origin. Usual relation, launch angle will be theta, launch speed will be v naught. And our question is, at what point in the trajectory will the velocity be perpendicular to the initial velocity? I want to know at what time that happens, and also how far apart, or rather how far from the origin, is the projectile at that time. So let's go ahead and use some vector geometry to work this out. I'm going to start by setting 0 equal to the dot product of v naught and v. That's what it means for two vectors to be orthogonal. Their dot product should be 0. Now v naught is some fixed vector. Okay, we'll probably have to figure that out. V, however, is given kinematically. Where here a is the acceleration vector, and of course we know that that's g in the negative vertical direction. Expanding out the dot product, get a nice relation like this. V naught squared is now a scalar. That is the launch speed squared. T is the time we're looking for in this first bit. I just have to figure out what the dot product between the velocity at this random later time is. Sorry, that should be a v naught, and the acceleration. Now remember, in general, the dot product between two vectors can always be written as the product of their magnitudes times the cosine of the angle between them. Magnitude here is v naught, magnitude here is g. Now I just need the cosine of something and multiply it by t. Now the angle I need to plug in here is the angle between my initial velocity and the acceleration. But as usual, since I've defined my launch angle, or I'm defining it now to be theta, and we know that the acceleration is in the negative j hat direction, we can see that the angle between the blue vector and the downwards pointing, maybe I should have put it here, red vector, is actually 90 plus theta. Okay, so this is the angle between my initial velocity vector and my acceleration vector. It's the launch angle plus an extra 90 because A points straight down. Let's do a little bit of trig to simplify that. Cosine of pi over 2 minus theta is sine theta. That's a cofunction identity. So cosine of pi over 2 minus theta, which is what we have, a plus theta, would be the same thing as sine of negative theta. So I'm using a cofunction identity there. And of course, sine is odd, so I can pull out the negative side, SIGN, and I can solve for t. We need that to be negative, so that when I divide it over, I'll get v naught over g sine theta. Okay, so that is our time. At this time in the trajectory, the velocity will be perpendicular to the initial velocity. Notice that that's assuming that it actually makes it there. For example, if for some reason the trajectory ended earlier, it would never find a time when those two velocities are perpendicular. Okay, using this time, I now want to find how far apart are, how far from the origin is my projectile at this time. So let's see, maybe we're over here somewhere. We can see that our velocity vector here is orthogonal. I tried to make those look kind of perpendicular. And now I want to know what's this distance. Maybe I'll call it d. All right, well, Pythagoras will give us that. D squared will be x squared plus y squared. X and y being the components of the position of the projectile. And we know those from kinematics also. Squared. Okay. The t that we just got is what we're going to plug into both of these because that is the time when these are orthogonal. Doing that, will give me what? A v naught squared, because there's v naught here, over g, that is a distance, cosine over sine squared. And of course, cosine over sine is cotangent. So that'll be my first term once the t has been plugged in. For my second term, this first bit will become a v naught squared over g. The sine theta here and the sine theta there cancel. And the second term will become a v naught squared, when I square this out. G over g squared will give me 1g in the denominator. There's still a 2 there, so I'll leave that. And then there will be a 1 over sine squared, which will be a cosecant squared. Okay, now let's try to factor as much as we can out of this. So d squared will be v naught squared over g squared shows up in all of these terms. So I'll just pull that all out to the front. V naught squared over g quantity squared. And then what's left inside is going to be a cotangent squared, a 1. Don't forget we're squaring this whole thing out, so we got to be a little careful. There'll be a 1 from this one. There will be twice the cross term, so that'll get rid of this 2. And I'll have a 1 times a cosecant squared with a negative sign. And I will have a plus 1/4 cosecant squared. Okay, but the square has gone away. Okay, now we just have to simplify as much as we can. Oh, sorry, this should be cosecant to the 4th, because it was squared and then squared again. There we go. But look right here. Cotan squared plus 1 is cosecant squared. That's one of those Pythagorean trig identities. So these 3 terms cancel. Okay, finishing it off then, maybe I'll cheat a little bit and go up here. We see that when we take this square root, I'll have v naught squared over g. The 1/4 square rooted leaves behind a 2. And then the cosecant to the 4th square rooted gives me a cosecant squared. And that is the answer to the second part of this. The distance the particle is from the origin when its velocity becomes perpendicular to the launch velocity is given by this expression. We've seen this kind of structure before. V naught squared over g is kind of the only units of distance you can make out of these types of problems. Sometimes there's a 2 down here, sometimes there's not. Sometimes I have a cosecant squared like we have here, or a sine squared like we did in the maximum height case, or a sine 2 theta in the case of the range, or some trigonometric function there. But I thought it was interesting that we can find one that has a cosecant squared. So there they are, the time and distance for the projectile when its velocity is perpendicular to launch. QED.